as we're working our way towards the last major subject in fluid dynamics that we're going to cover, which is Bernoulli's equations or fluid flows, we're going to look at one interesting little consequence of fluid flows. And we're going to deal with a little bit more specific case of a fluid. And that is, we're going to look at an incompressible fluid. There are compressible fluids, but in this case we're going to deal with predominantly incompressible fluids. And most liquids do this. A lot of gases in a lot of situations, for the most part, are incompressible as well. They flow in a way where the density of the fluid doesn't change as it progresses through its path. So what we're going to look at is what's called the continuity equation. And you'll see this idea of a continuity equation show up many times in physics, and this is probably one of your first times seeing it. But really what it says is that the area of a fluid at one point in a pipe or one point in its flow times the velocity at that point has to be equal to the area at another point times the velocity at that point. Well, it's really, this sounds a little bit complicated. It might take your head a little bit to get around it, but it's nothing more than saying that the molecules don't build up in the flow. If you enter a pipe, you leave the pipe. If you enter a vein, you might split off to different directions, but eventually all the blood that's going through your veins is going to come out of the other side wherever you're looking. So we start off with some volume or some area. The area and velocity, and it's going to go along this path along a pipe. It gets to the other side, it's going to have a different area and a different velocity. Well, this quantity A times V, the area times the velocity, is known as the volume flux, or volumetric flux. Designate with a J. You may see it, you may not. But what it just means is that the volume of the fluid flows through one section of pipe, it's going to flow through another section of the pipe. Or the volume per unit time is another way to rewrite this equation. So if we have this volume here, and we look at it, it takes so much time for it to get past this front edge. Well, if we look at another point along this, it's going to take the same volume, the same amount of time to flow through. So the velocity for smaller pipes will be larger to compensate for the smaller area. So area times the velocity is a constant for an incompressible fluid, assuming there's no sources or what we call sinks, so no way to add in extra volume and no way to subtract out volume from this, so assuming the path doesn't split. So again, another form of this that you see is that the volume over the time is equal to the different volume at the same time. These volumes per unit time have to be equal.